At this point in class, we already know that current running through a wire, when it's in an external magnetic field, feels a magnetic force. In this lab, we're going to figure out how the length of the wire affects the size of that force, the amount of current running through that wire affects the size of the force, and the strength of the magnetic field that it happens to be in also affects that size force. So for this lab setup, we just have a simple setup where we're going to have different lengths of wire, and we're going to use a power supply to force different amounts of current to flow through that wire. So we have this side being at high potential, this side being at low potential, and so conventional current will flow from high to low potential. So we're going to have current flowing in this direction. Now, it's only going to feel a magnetic force if it's in the presence of a magnetic field. So to do that, we're going to use this. So we have a couple iron strips right here and a small gap in between them, and there's some small neodymium magnets all facing the same direction on either side of that gap. That little black dot indicates a north pole, so these guys are south poles. So in between this gap right here, we're going to have a really strong magnetic field pointed to the left. And then we're just going to raise this wire up and put this wire in between that gap. So when we run current through the wire in this direction, there's going to be an external magnetic field in that direction. And if we use our right-hand rule, let's think about this. We're going to have the external magnetic field lines pointed to the left. The current is going to run in the direction of the thumb, and the wire is going to feel a direction in the direction of the palm. So the wire is going to feel pushed up with some amount of magnetic force. But let's think about this. If the wire is feeling pushed up, Newton's third law suggests something must be pushed down. Well, what is that something that's being pushed down? Well, what's pushing up on the wire? The magnets through the magnetic field are pushing up on the wire. So when the wire feels a push up, the magnets in this thing will feel a push down. Well, we have this on a little electronic balance. You can see that it's got about 109.69 grams worth of mass based on the gravitational force that it feels. And if the magnets and this thing feel any extra push down, the apparent mass is going to go up. Based on that apparent mass change, because this is on the Earth, and we know the Earth's gravitational field strength is 9.81 newtons for each kilogram, then we can figure out the approximate amount of magnetic force pushing down on this, which has got to be the same size as the amount of magnetic force that wire feels. So we're going to use this same setup for 3 different experiments. So experiment 1 will be looking at the effect of changing the current, see how it affects the size of the magnetic force. Experiment number 2 will be changing the length of the wire in that magnetic field using a constant current, and we're just going to crank it up to use the largest current that this power supply can provide, which is 5.3 amps approximately. And then the third experiment, we're going to use the highest current possible, the longest wire possible, keep those things constant, and then we're going to change the number of neodymium magnets attached there to vary the strength of the magnetic field, and we're going to make the assumption that the magnetic field strength in between those 2 iron strips is proportional to the number of magnets. So when we use double the number of magnets, we're going to have double the magnetic field strength. Then we can look at the result of all 3 of those experiments to find out, hopefully, an equation that allows it to calculate the size of the magnetic force on current running through a wire when it's in the presence of a magnetic field with a known length. One last note, for the data collection videos, we're going to actually zero the electronic balance when there's no current running through there. So if we hit 0, instead of 109.7 grams, it just says 0. So if we increase the current, or if there's a magnetic force on the wire and therefore a force pushing down on the magnets, that value right there, the additional apparent mass, you can use the Earth's gravitational field strength to calculate the approximate magnetic force felt on that current carrying wire.